Well, it looks like we can start. Welcome back, everyone. We've got a pretty balanced class today, 2 in person, 3 in the Zoom side. I'm glad everyone made it in today. For the class like this, where most of the section's fully online, sometimes there's kind of, looks like as the semester goes on, kind of a wants to just participate by looking at the YouTube videos. And if that's working for you, I'm not going to judge anyone or take off credit or anything like that. There's no kind of attendance or participation policy. If you ever feel like the course is getting pretty hard to follow along, participating by just watching recorded lectures on YouTube, then definitely come to class. I'll be happy to assist further. Sometimes just being in class, whether it's in Zoom or in person, just is a better way to engage with the material, participate, and have it really absorb. It gets better traction on your mind versus sometimes watching a YouTube video feels really, really passive. But for anyone in the class, whether you're reviewing an old lecture or anything like that, if a question comes up from something you saw maybe in chapter 2 way back in the day, you can always just send me an email and say, hey, Mike, on that video stamp 43 minutes and 50 seconds, what were you saying there? And I'll be happy to go back to that and clarify. But welcome back, folks. I'm glad you all made it in today. The big announcement is just kind of a refresher on what we were discussing Monday about the upcoming exam one. Instructions were sent out on Monday for scheduling your exam at your preferred testing center if you're in the online section. And for the in-person section, we'll just be back here a week away from today, Monday, February 9th, and we'll have the we'll have the exam at 1 p.m. in class. So maybe just to reiterate a little bit more, just for the sake of, this is our first exam, so we should really talk about how should we prepare to study for it. Because we don't have any review days designated for this class, in my sense, I feel like for a great sense of fairness for exams, the exams are going to be very similar to what you're actually doing in the exercises, which is very similar to what we did in the lecture notes. Aside from the fact there's no RStudio calculator, so you don't have to bring like a laptop or a desktop computer. So any output that came from here, whether it's a graph, a histogram, box plot, or maybe a normal probability computation, it's already on the exam itself. And your job is just to give a conceptual answer to the information that you see there. Oh. So take a look into, sorry for undoing that again. Take a look into either versions of the sample exams to get a good feel for what do the conceptual questions look like. And if you're fully caught up on these assignments, then I promise you this exam is not going to go out of scope of what you actually did in the homework. So as far as grading goes, I'm going to be grading these assignments pretty much the moment I have a free time and the moment I get your assignment. So once you submit, I'll get that graded. I'll upload your results to Canvas, check out the PDF it gives you. And even for assignment 4, thanks to the person in class who mentioned, the due date is not February 9th because we're finishing this chapter today. So the due date will be a week away from today. But that's just the pattern we're doing on all of our assignments. If you get assignment 4 done and you want to turn it in early, I'll make every effort to have that graded and returned back to you before we come into the exam on Monday. If you get your homework, say, even on Sunday, even late on Sunday, I'll be grading them first thing on Monday, try to get through as many as possible. I should be able to get through the whole set, hopefully, so you can get that feedback ahead of the exam. But that's pretty much it for the announcements. We're going to return to chapter 13. We're on the last example. I'll turn it over to the class at this point. Any questions or comments at the moment? Okay, well, let's begin. Maybe one more comment for the announcements as far as assignments go. We've mentioned before in class, but it doesn't hurt to reiterate. Everyone essentially has a extension policy that's automatically applied to all these assignments. So even if you don't get assignment 3 turned in just today, that's okay. We'll get it done as soon as possible. And you're not going to get penalized on anything being late. Even if you dumped every single assignment on me on the week before the final exam or the day of the final exam, I'll accept all of them and I'll get them graded. It'll just take a bit for that. It's probably not the best practice. Definitely want to get these assignments done to help out with the exams. But if you're a little bit behind, no worries. Just get into the course as soon as you can, get those assignments completed, and I'll accept all of them for full credit. So here's where we left off in chapter 13, the sampling distribution chapter. We were looking into the central limit theorem. And so let's maybe pause here for just a moment and think about this once again, now that we're coming back a little bit fresh. Lots of stuff happened on these notes that were pretty abstract. So the reminder of the central limit theorem, there's two versions of this theorem in the chapter 13 notes. We're going to get into the one that deals with population proportions when we're in the later chapters. So if you read that material, you wonder why it's not in the notes. It's only because we didn't have an opportunity to use it yet for a couple chapters. So we'll return back to the chapter 13 content to get to the central limit theorem for proportions, And this is the central limit theorem for means. It says if you have a simple random sample that comes from any population with a finite mean and standard deviation, then if your sample size n is large enough, the sampling distribution of the statistic x bar, that's a probability model from which x comes from, will be approximately normally distributed. For large enough values of n, that approximation gets better and better. And this is the quick and interesting little graphical summary we did of the central limit theorem. We had a psychological experiment with a particular mean, 148 milliseconds. Standard deviation is large, 105 milliseconds. And it was, as the author called, violently skewed. But as the sample size gets larger and larger, what you're seeing here is the sampling distribution for y bar. Again, that's a particular way that this textbook wrote out their statistics. So when you see y bar in these notes, y bar will be synonymous with x bar, which is the sample mean. I had to write it in as y bar because that's how the author worked their graphs. Some textbooks do x bar as ours, and some do y bar for their same object. So here are all sampling distributions we would expect. Coming from this, we're assuming is a population now. As the sample size gets larger and larger, notice how the curves are approaching normality. And if this kept on going, if the sample sizes, say, got past 1,000, it would get to the point where this looks pretty much just exactly like the normal distribution. So that's the big idea with the central limit theorem. It's duplicated a bunch of times on the notes because of its importance. And we're nearly done with these notes, but we're going to finalize one last example thinking about this theorem from now the computational side of it. But any questions at all, folks, with the refresher? Okay, so here's our last question of the notes. This scenario says the scientists at the Hopkins Memorial Forest in the western Massachusetts have been collecting meteorological environmental data for more than 100 years. So they have some extensive knowledge on what's going on in this area. And they tell us if we look into just the past few years, sulfate content in water samples from Birch Brook, that specific location, has averaged 7.48 milligrams per liter with a standard deviation of 1.60 milligrams per liter. So we're looking to specifically sulfate content. And here's the statistics we have from this population. Here, this didn't come from a sample. This was just all of the data they had, and they're giving us a value. So this is multiple samples over the past few years. It looks like it's indicating. What we're going to be doing is modeling the population sulfite contents of Birch Brook with a best guess of a parameter, the population mean being 7.48 milligrams of sulfate per liters of water, and standard deviation 1.6 milligrams per liter. Okay, so that's our statement of the problem so far. Now it makes a big assumption. It says, assume the population sulfate contents can be well modeled with a normal distribution. I mean, that is a big assumption. We're not saying this time, though, that it's exactly a normal distribution. We're just saying that if we took a whole bunch of measurements and looked at the sulfate content in meters per liter, it's symmetric. It's probably unimodal. It probably has a nice mound shape or bell curve shape, but not perfect. We're not saying it's exactly normally distributed. It's just well modeled by a normal model. So that's a pretty big statement there. And that's okay. This says we can deal with any population. It doesn't have to be exactly normal, but the more and more skewed that population becomes, the bigger the sample size is going to play a role in this. We say it's well modeled by the normal distribution, and we have a sample size of, say, 10 measurements. That's probably going to be okay for the central limit theorem. We shouldn't run into any challenges as long as that's an accurate assumption. So it says we now have a simple random sample of 10 sulfite measurements gathered. And so imagine that's 10 different graduate students in different regions of Birch Brook, because we want a representative sample of this region geographically. They're out in the field and we know that they have the 10 samples, but they haven't come back yet. So we don't actually know the value of the statistic this time. This time, X bar, the sample mean, is unknown. So we're imagining they haven't come back yet, and once they do eventually all arrive at the lab, we'll have a value for that. But even with this unknown, we can make some interesting computations relative to the unknown statistic. So other piece of information was we have a random sample. We're told it's a simple random sample. So probably a lot of work went into that, but the sample size is 10 measurements for sulfate. So putting all that together, here is the question that is pretty confusing when you see it in a homework assignment, or if you see it, say, in an exam 1 setting. If it's talking about a sampling distribution or approximate sampling distribution, here the idea is, maybe a color is not a good idea for that. Let's just underline it. We're just thinking of the central limit theorem, especially because we said the mean. We're not talking about just one measurement, say capital X. We're talking about X bar itself, the unknown this time. Let me just fix this pencil real quick. Okay. So by the central limit theorem, feel like a good abbreviation for central limit theorem. This is the standard one, CLT. By the central limit theorem, the mean of those 10 observations, X bar, will be distributed normally. This is an approximation, so I'll make a statement at the end just to emphasize that. It'll be distributed normally. The true mean, if that's an accurate parameter, is 7.48. The value we're using to model the underlying population. The standard deviation will be 1.60. But that's not the whole story. That's this part, sigma. We threw in that part's mu, but we can't forget to divide by the square root of the sample. So the variance is changing on this. It'll be divided by square root n, which is 10. And we could say here, approximately, just to be honest, this is not a perfect distribution, but we believe that this one is going to do a really great job based on that statement there in yellow, and the sample size being small is a concern, but not with that yellow statement. So I'll say here, approximately. Okay, so that's the abstract content of part A. But now that we have a probability model, any probability question we ask is pretty fast to answer. It asks, what is the probability that the mean of these 10 measurements, again, they're referring to X bar each time they say that, will fall between those values, 6.49 and 8.47. And let's pause and address the question of why would we want to compute this? Remember, there's a sample of 10 measurements and they have been gathered. They just have to come back to the lab, determine the sulfate content in meters per liter, and they'll know the exact value of the sample mean of those 10 measurements. So why would we want to know this probability? It's because things can go wrong. We can now answer what if scenarios. If the 10 measurements come back and we get a really, really strange value, say 13 milligrams per liter, we might be very, very shocked about that. And so we might want to know, what's the probability it falls between these two values? If that's a very, very high probability, yet the mean of the sample comes out as, say, 50, just something wild, we might say something has gone wrong. Maybe the sampling design was flawed. Maybe the measurement collection process went bad, or maybe these parameter models are completely off. Maybe the normal distribution is no longer in effect, something has happened in this environment, but we will know something has gone wrong. So before we even conduct the study, before we even send people out to gather the sulfate measurements, we can ask, what's the chance that the output of the sample mean falls between these ranges? So we can write out the probability statement as probability, start with 6.49. Units just to remind us of the context. Less than, it's the mean of the 10 samples, so X bar comes back into play. Less than 8.47 milligrams per liter. That's milligrams of sulfate per liter of the water. And now we can throw this into the calculator and get a value. So the syntax for this is good to start with just putting in your model. I guess I'll leave it right here. Start with the mean. In ordinary words, I would just say mu is 7.48. I'll write sigma is 1.60. And if you put this whole value in, that'd be completely fine. So let's go divide by square root 10. So that's the entire model. We have the sample size built in. If you want to see what happens as you change sample sizes, you could put the sample here on the very top and put n there as well. But let's go with this, just the specific 10. We're thinking of this syntax as just being run once. So now we're going to answer the part B question. We use the pnorm function, pnorm 8.47, and then just put in u and sigma values we specified. Then subtract this pnorm at 6.49, mu and sigma, and assuming I didn't make any errors with the syntax, this should run nicely for us. Let's see what we get. I have a value altogether of 0.9496. I'll round this one to 4 decimal places, but you know it's basically 95% if you rounded it to the nearest hundredth. So 0.9496 is the value. So the practical interpretation is essentially the question now. We can say, if we approximated, there's approximately a 95% chance that we take a simple random sample of 10 measurements, calculate the sample mean will be between these two figures, 6.49, 8.47. So that's a pretty high probability. That's saying essentially 19 times out of 20 almost. So if the students come back, maybe graduate students and such, and the sample mean is within that range, we would say nothing too unusual happened. But if the sample mean came out as, say, something small like 3 milligrams per liter, or something gigantic like 14 milligrams of sulfite per liter, then our eyebrows are going to start to rise. That's suspicious by what the central limit theorem is telling us, based off these parameter values. So that's a direct use of a central limit theorem problem. It's a great tool for what-if analysis. What if this is really accurate values and we go to gather our sample? What's a plausible range of values we would obtain? Any last questions at all, folks, running through that computation? Okay, and the last part of this, part C, is just an acknowledgement that a lot of things can go wrong. It says here, what do we need to assume for the probability calculation just made to be accurate? Well, we said it's dead on accurate, but that's not completely honest, right? The model was an approximation, so if you put this here, that might have been a better way to say it. I'm not going to be super picky on that. If you wrote just dead on equality, that is okay. But this is just acknowledging a little bit better that it is an approximate probability. And for this to be an accurate approximation, let's mention, it says here, at least 2 assumptions. And I'll go first. One massive assumption that has to work for the central limit theorem is at the very top, we really have a simple random sample. So if all 10 students, say, got out of the bus or truck, and then they just walked up to Birch Brook, the most convenient spot, and everyone grabbed a sample from that one spot, we have completely violated the most important assumption of the central limit theorem. And that might be one reason why the sample mean didn't fall between these ranges. That 10 observations wasn't representative of the entire region of Birch Brook we were concerned about. So for accuracy in this statement up here, we require the sample was representative. In other words, it came from a simple random sample. The simple random sample is the gold standard in sampling using the central limit theorem. If I put here representative, since occasionally we're not sure if it's exactly a simple random sample, but if we know it's at least representative, then it's not perfect, but we still probably have a pretty accurate computation below. So it says at least two things. Anyone see another thing that must happen for this to be fully accurate? There's a lot we could say. So if you're not sure, no worries. It's kind of a wide open question, really. Well, here's another thought that I would go to for the next item. For me, the next biggest item was that right there. Because notice our sample size is small, just 10 observations, a lot can go wrong. If the sample size was, say, 200, I would be less worried because I think in actual practice, it's hard to come up with a distribution that is violently skewed to the point where a sample size of 200 is not effective. This is a really bad one, but yet at sample size 128, central limit theorem would do a good job despite this small skew we see. So at sample size 10, here's what could go wrong. You might have a population that looks, say, like this. Let me see if it's somewhere here in the notes. That's going down. There we go. If your population is skewed like this, if most measurements of sulfate are pretty close to, say, the mean value, but then you have some extreme values depending where you are on Birch Brook, 10 observations aren't going to do it for the central limit theorem. So the next thing I would probably say is, since the sample n equals 10 is small, doesn't mean we can't do anything with it, but it means that is a really big assumption that has to check off. We'll say here, we require the population. That would be all potential measurements at all potential locations of Birch Brook that we're interested in. That population must be symmetric and unimodal. And this is a run-on sentence. And you could say bell curve shape. I'll just say briefly, mound shaped. I think mound shaped kind of ties in unimodal, but it doesn't hurt to really kind of get that mental picture in by saying mound shaped with unimodal. You could definitely abbreviate that a little bit by just saying mound shaped. And those would be, to me, the two biggest things. For mentioning just two items or two assumptions required in the central limit theorem, those would be the big ones. The other ones I've hinted at as well are we made massive assumptions about the population from the very beginning. And maybe they're trustworthy because they've been working really hard on these measurements for 100 years, we've been told. But things can happen. Geological events could occur. Who knows what could happen to the population today? They shift with time, not just location. So the next big assumption is that these two parameter values are still accurate for the population. Let's mention them. It said at least two, but let's put in the three. The values for mu and sigma are still accurate when the study was conducted. So if these big ideas here work out, then we have some pretty good reliability on what we said here. It's not perfect. And the more and more any one of these assumptions break, the less and less we can trust that value there. But any last questions at all, folks, with the conclusion here on chapter 13? Okay, well, this is the end of the content for what we'll see on an exam one situation. But the good news is, as we turn to the next chapter, we're not done with the central limit theorem. We mentioned we're getting into introduction to inferential statistics. Probability and the central limit theorem are what brings us into our methods starting off in chapter 14. So the due date on this is pushed way back. We'll possibly finish this when we come back Thursday after the exam. If we need to take a little bit extra time because there's lots of big ideas in chapter 14, we'll do so. It's an introduction to statistical inference, but we're at the part of the course now where if you have taken an introductory statistics class already, this is still good stuff. This is probably going to be a really great refresher that will be running through in chapter 14. And if statistics is brand new to you, no worries. We're going to look into this in a high level of detail. Chapter 15 is going to say a little bit more about margin of error, and a little bit more about hypothesis testing, type 1, type 2 errors. And then the course really starts running in chapter 17, 18, 19, and so on. That's where we're going to do our big, heavy-duty statistical methods. So since we're still introducing inference, we're just beginning the topic of statistical inference itself, we're going to make what the author calls simple conditions for inference about a mean. These are not conditions used in practice, but for the purpose of learning about inference for the very, very first time, they're appropriate condition or assumptions to make for a classroom problem. And we'll complain about the problems with the assumptions we make, the conditions on this, as we go through the problems and see how we fix them when we're in chapter 17. So for the moment, because it's an introduction, these conditions aren't fully acceptable in actual statistical practice, but that's just us getting started. I printed the central limit theorem here just as a quick reminder. We're going to need that in a moment. But in chapter 14, let's look through these conditions. We're going to assume we have a simple random sample from a population of interest. Again, that's the gold standard, but a lot of problems we look into, all we know is that the sample is random. We don't know for sure that it is 100% certifiable, a simple random sample. Sometimes it gets even worse. Some studies just simply tell us we have a representative sample, and that's where your eyebrows and hackles should go up a little bit. That's where you want to really read the methods and see if you believe that it really is representative. So in some of the statistical problems we look at, we won't actually have a simple random sample. It'll be up to us to judge if the conclusions we make are appropriate. The next condition we're going to make is our population came from an exact, perfect normal distribution. Now that's the part where we're going to be able to take that off pretty fast in chapter 17, because we'll just start to use essential limit theorem. So we can navigate through this one. It's easy to peel off that assumption. But for just getting started in chapter 14, that's an assumption we'll make. And finally, this is an assumption we'll make whenever we're doing any hypothesis test or confidence interval relative to a population mean mu. If we're estimating mu, we don't know it. But this is the really, really weird one. We're going to assume a value for sigma. And that's an assumption we'll take off right away in chapter 17. But for the moment, for just getting it started, we'll say that's a reasonable assumption. And if we don't exactly know what sigma is, we'll approximate it with the sample standard deviation S. Historically, that's what people did. And they noticed when samples got really, really low, that's a tremendous problem. When samples are, say, 10, 5, 4, 3. But that's an assumption we'll make just to get started. Well, any questions at all, folks, with the simple conditions for inference? Okay, now example 1 is the connective glue between normal distribution, central limit theorem, and statistical inference. So it's a kind of exciting an example in a certain case. Here's where the central limit theorem is going to make a comeback. Let's run through this quickly, or not quickly, excuse me, carefully, and see how it goes. Consider a population that has an unknown population mean, mu, so that's good. That checks the logical assumption we would make for any test. And a known population standard deviation, sigma, so that's the weird statement there. We know sigma. Let's highlight that there. So we have an actual numerical value for sigma, meaning we can compute with it. Further assume, it says, this population is distributed normally. So that's assumption 2. Again, that could be weakened if our sample size is large enough through central limit theorem. So we're not super worried about that one. And it says next, our goal is to estimate the population parameter mu. And we can do that. You gather your simple random sample, calculate the sample mean, and there's your approximation right there. Let's highlight that parameter, the typical color we use. So the parameter is well approximated by the mean of the sample, but this is not good enough. Like we've mentioned quite a lot in the notes, we must determine the margin of error in that estimate. And if we can't give people the reliability, the precision in making that estimate, the margin of error set differently, then it's effectively useless to us. But we can't do this at this point. That's kind of exciting in a certain sense. We're going to approximate this error right here and now. So just imagine a random population, could have been, say, Birch Brook once again. We're going to assume we know sigma, mu is unknown, but the central limit theorem is going to give us some values right away. We know that value mu, excuse me, sigma, that's highlighted there, not mu. So we can say by the central limit theorem, CLT like we used before, X bar is going to be distributed normally, and we don't have to say approximately normally if this is the verbatim literal truth of the population, exactly distributed normally. It'll be distributed normally with a mean mu. That's the unknown we want to estimate. And the standard deviation will be sigma divided by the square root of the sample size n. And we can fully compute this value right here. This is going to get us started now on computing the margin of error. So I haven't done too much about this problem except read through it, indicate our goal, and then pretty much directly cite the central limit theorem from above. But now that we know we're dealing with a normal model, we can go back into chapter 11 and use this concept. So chapter 11 had the empirical rule. We never use this for computation because we have more powerful tools, RStudio. But for the sake of just a concept, like coming up with margin of error, this is a useful tool to have. It tells us if we are modeling data with a normal distribution, we expect that, I'm going to use line 2, approximately 95% of the area, and then that's going to be probability for us, will be within 2 standard deviations of the mean. So let's cite this directly. So this is the empirical rule from chapter 11. So when it says 2 standard deviations of the mean. Let me fix this for the sake of highlighting. We're referring to that entire thing as the standard deviation. Then we say of the mean, we're referring to mu as being the mean. And the thing that we're modeling is the sample mean x bar. So we can write down a pretty profound probability statement now. By that rule above, we can say the probability that the distance between the known value, the sample mean, and the unknown that we actually want to estimate, it could be written like this. X bar, let's go mu minus x bar. The distance between them will be within 2 standard deviations. So here's the 2 in that problem. And when it says standard deviations, that's sigma over root n. That probability is approximately, we can make that much more accurate if we use RStudio. Let's just go with the approximate value to focus more on the concept. 0.95, so a 95% chance. So mathematically, when you see that absolute value bar, we're talking about the distance between when there's a minus in the middle. So this is just saying the distance between the parameter mu, which we want to calculate, and the statistic, which we have a number down for, will be within 2 standard deviations. So we've connected the dots of the central limit theorem. We directly use the normal model with an approximation here for the 95% as a probability 0.95. Now we'll rearrange this a little bit and come up with our margin of error. Well, that pretty much is the margin of error, but we're going to rearrange it just for the sake of tying this together with the formula for the confidence interval. But any questions so far? Okay, because there's lots going on inside this interval, let's do a little bit of algebra for the moment, focusing on this absolute value. So if we write absolute value of mu minus x bar less than 2 times sigma over root n, that would imply we have a triple-sided inequality. You take the negative of this side, negative 2 times sigma over root n, will be less than the thing in the middle, mu minus x bar, will be less than the right end, but positive now, 2 times sigma over root n. So the left side and the right side are mathematically equivalent. The arrow is just saying the left side implies this new triple-sided inequality. The thing that we want to estimate is mu, and it's right there in the middle. All we need to do is add x bar to both sides, all 3 sides rather. So this will be, add a positive x bar to the left, it'll be x bar minus 2 times sigma over root n, is now less than mu, which is less than x bar plus 2 times sigma over root n. And this is what the central limit theorem allows us to do. Mu is the real unknown here. We're going to calculate x bar in practice when we look in our statistical methods. We can place mu in the middle. We have these values are telling us the range that mu can take when we take the simple random sample. It's from x bar minus that value plus that value. And this is the margin of error. So to summarize, we can now say the probability the x bar minus 2 times sigma over root n is less than the thing we want to estimate, mu, the mean of the entire population, without actually taking a sample, which is the entire population, so no census involved. We'll know it's between these 2 values. Now, x bar plus 2 times sigma over root n. Notice the logical flaw in that, though. You had to assume you knew the standard deviation of the population. And a very fair question is, in what context is the mean of the population unknown, yet the standard deviation is known? That's really, really rare. But there are contexts where that happens. For example, In IQ testing, we don't know the mean of the population, but the IQ test itself is standardized. So sigma is, I believe, 10 or 15 points. I forget exactly the right value, but some standardization can happen in the right context. Most of the time, though, we don't know mu and we don't know sigma. We're going to need to fix that logical loophole, and that's what we will be doing in chapter 17. Well, to summarize, this is going to be equal to approximately 0.95, and now the approximate error in this estimate is the margin of error in the estimate, mu approximately equal to the mean of the sample, x bar, is m equals 2 times sigma over the square root of n. And you could say plus or minus if you prefer, that'd be completely fine. But for margin of error, I'll focus just on the positive value. And the last concept that we're going to be looking into really shortly is that x bar plus or minus 2 times sigma divided by square root of n is an approximate 95% confidence interval. So this is what we mean finally by inferential statistics. All we have is a simple random sample. Then we calculated a mean, x bar, but we're using that mean to describe the entire population when we do this estimate. But when we do that description there, it's inferential statistics. And at the same time, we need to describe the error in describing the population through x bar. And it's right here. The margin of error is 2 times sigma over root n. We have some big problems to resolve. We need a better number than roughly 2. That came from this, the empirical rule, and that's a fast one to fix. And the second logical error is, what do you do if you don't know sigma? You could put the sample's standard deviation there, but now you have an approximation on that as well. It actually causes a big change in the probability model, and we'll look into that on chapter 17. Well, any questions at all, folks? Connecting all those dots from chapter 11, 13 into chapter 14? Okay. Well, the first thing we're going to resolve is that 2 you see here and here. Let's highlight it. That number is the approximate critical number Z star is the way our author denotes this. And we can fix that right away. We want to be as accurate as possible when we give the confidence interval. And this is our first starting point. Really, it's going to be a chapter 11 method for us once again. So the critical value, I called it number. Let's say that's a synonym. Whether you call it a critical number or value, I'll try to say critical value more often than not. The critical value Z star is the number that catches central probability C under the standard normal curve between the negative critical number and the positive critical number. That's what we have going on here, a negative critical and a positive critical here and here. When it says probability C, that's this stuff right here, the probability we're trying to output. We're going to call that later the confidence level C. So, in other words, the probability statement is, if Z is distributed with a mean 0, standard deviation of 1, then on the standard normal curve, find your critical number to capture the central probability at C, and we'll call that the level of confidence in the estimate. This one was an approximate 95% confidence interval. And computing these actually turns out to be really, really fast. It goes like this. You put down a really fast normal curve. This is N01, And even if our mean and standard deviation is different, that's okay. This is just counting standard normal distributions. And so the same value will apply to any normal distribution. We'll just say how many standard deviations you have to go away from the center, whether it's 0 or 5, and whether the standard deviation is 1 or a million. So we're capturing in the center here, central probability. When we say central probability, we mean symmetrically around 0. Going from here to here, we'll have 0.95. That's our confidence level. So if 95% of the area is here, you would get, in this tail, 1 minus the confidence level, or 1 minus 0.95. Well, that's both tails at once, so you would just divide it by 2. So in this problem, it'll be 1 minus 0.95 divided by 2. So that would be, say, a 2.5 here, a 2.5 here, giving us the total of 1, or 100% for area. And to get that value, that's pretty quick as well. This is negative z star right here. This is positive z star. And if I want to get that area, this will just be a Q-norm operation. So we can say z star is Q-norm. You can either put 1 minus 0.95 divided by 2, but you know a really nice trick here is confidence levels can change. Let's just put it in this way. 1 minus your level of confidence divided by 2. If you use that syntax, you will in fact get a negative z star. And that's actually okay as well, because you'll always have a negative z star and a positive z star, because there's a plus and minus in the interval method. But it just looks weird giving a negative z star, so we can fix that by going lower dot tail equals false. Or you could just put a negative sign right in front of Q norm if you want just more cleaner looking syntax. It'll give us the same effect. So we'll use use the table below to complete out example 2. The work in RStudio, I think I forgot to do one thing. I'm going to put that in the notes in chapter 13, so let me open a new tab. I'll come back to that after class is over. It's probably not the good use of class time, watching me upload that to the notes. I'll make sure to share this syntax. First thing you'd want to store is the level of confidence you're about to compute. So I'll say C gets. Let's start at 0.90, 90% confidence interval. Then Z star. I'll often just write it this way in the syntax, because if you try going this way, I believe that's going to come up as a syntax error. You can't put a star on this one. That's the multiplication operator. So Z star will get the output of, following the guide down below, Q norm. I have too many parentheses. Let me start over with that. Q norm, 1 minus confidence level divided by 2, lower dot tail, equals false, just to get the positive value. So if we run this, let me put in one more Z syntax. Z star is to the right, but I'm usually looking down the bottom, so I want one more line just to make it output. Z star comes out as 1.6449. So it's telling us if you go about 1.6449 standard deviations, you're capturing the central probability of 90%. So 1.6449. Let me double check my numbers on that. Yeah, rounded to that place. Well, any questions at all, folks, on getting the first row? Okay, again, if you've left your syntax like this, you'll get the same value, just opposite in sign. You're actually getting that Z star there. So when I said lower dot tail equals false, it's actually getting the area to the right, just producing the positive Z star. A negative sign does the same exact effect if you prefer to go that way. So there's your positive Z star. I mentioned we're usually going to be using in this class lower dot tail equals false, and I'll keep on doing that just for the sake of parallelism. So now let's bump up the confidence level to 95%. That means we're looking into this approximation. We said our critical number was 2, so now we're wondering how far off are we? So let's bump this to 95, rerun the whole thing. And there it is, 1.95996. This is rounding with carrying, which is kind of annoying. But this is a number you might have recalled if you've taken a statistics class. This is 1.9600 rounded to 4 decimal places. And now we know when you round that to just a 1.96, that's actually a pretty accurate figure. So this is really, say, 5 significant figures. This has accuracy all the way to the 4th decimal place. Well, let's do one more. Notice the more confident you want to be, the larger the critical number. And logically, that might make sense because if you want to be more confident, your interval needs to get wider and wider and wider to have higher confidence. The method actually contains the unknown mean mu. It won't contain it as a guarantee on any confidence interval whatsoever, unless your confidence interval is the entire real number line, but that's useless to us. So higher values of confidence means less precision. The interval is wider and wider. So there's going to be a trade-off between confidence in the method actually working, containing the unknown mean, and precision, having the interval with a margin of error that doesn't explode. 95% is a good trade-off, but so is 94% or 96%. Humans just tend to like rounder numbers, so 95% comes up a lot. But if we're in a context where certainty is more important than precision, if we want to be more confident at the expense of a wider interval, maybe bump up the sample size to contain the width. Notice that contains the margin of error to a degree. But here's our punishment for having a high level of confidence at 99%. The critical number is getting big, 2.5758. And there's a mathematical limit here. As C gets larger and larger, their critical number Z star tends towards infinity, and that's kind of unfortunate. We can even see it on the syntax. If we want a 99.9% confidence interval, critical number is 3.29. Now imagine it gets kind of ridiculous, 0.999999. It's now a 4. And eventually the software is just going to glitch out. If you try to be extremely confident, run this. Oh, it worked. It's giving us a number 7. Let's just make sure that software really glitches out. This is 100% or 1 to most people. And the software outputs INF or infinity. Really, it just glitched out. There's a number there, but this is too big for the software to work with at any point at this stage. But infinity is also a reminder. It is true as confidence increases, the width of the interval also increases as well. That critical number that goes here just gets bigger and bigger, tending off to infinity. But hey, at least we can get this one element down. We can calculate the critical number exactly. Other things we have to address is what to do about sigma. But we're ready to describe this entire method right here, the entire C% confidence interval. Any questions so far, folks, before we take a look at that method? Okay, so here is our first statistical method. Again, I need to be upfront. It's not the world's best statistical method. It's extremely limited in practical use. But for the purpose of introducing statistical inference, it's not a bad one to take a look into. So here it is. We'll call this the confidence interval for the mean of a normal population. The method says, gather a simple random sample of size n from some population having an unknown mean mu, get a known standard deviation sigma. Then finally, a level C% confidence interval for the unknown mu is of the form x bar plus or minus z star, times sigma over square root of n. So z star is the critical number, which at this stage, we can just do a table lookup to grab, but no harm in computing it fresh, especially if we have a weird confidence level, like say 93%. And I guess there's not too much more to say about that. That's the entire method. There's another way to visualize this if you like. You could also rewrite this by saying, in other words, you have x bar minus z star times sigma over root n is less than mu, which is less than x bar plus z star times sigma over root of n. One thing that's kind of unfortunate with the formatting of that confidence interval is it's written as briefly as possible, and sometimes we forget what we're estimating. The mu is the major thing that's in there, and seeing it this way is really helpful for when we come down here and provide a practical interpretation using the context. So we'll give this a start. We have a real problem that was conducted back in 2011 for example 3. This is real raw data we're going to analyze, 16 observations. And here's the context. First, we're told a little bit about nuclear waste. Radioactive cesium, cesium-134, 137, is a waste product of nuclear reactors that are used today, certainly in 2011. And a study examined the radioactive cesium tissue concentration of a random sample of 16 Pacific bluefin tuna. So from there, we do know that the sample size n is going to be 16, based off that statement so far. They were captured off the coast of California 4 months after the Fukushima nuclear reactor meltdown of 2011. You could just say for short, the meltdown in 2011, because there's not a lot of these, thankfully. We'll definitely know we're talking about Fukushima. So the context is there's a meltdown in 2011. Nuclear waste leaked into the ocean, and then 4 months later, they were looking into this fish because they are a big migrating species just off the coast of California, which feels like a universe away. They found fish with these levels of radioactivity. We need to put that into context. So we're told historically the population mean radioactive cesium concentration in bluefin tuna has been below 2 becquerels per kilogram. So that means these are concerning values, right? These fish were quite radioactive. Now, I don't know enough about this unit to say, are they dangerous to eat? Are they glowing? I can't answer those kind of questions. But we can answer the question of, could we detect a change in the population just 4 months after the meltdown? And it looks like that's a yes. These values are all larger than the historical value, below 2 becquerels per kilogram. The question says, do these data provide significant statistical evidence that the mean radioactive tissue concentration in those fish is above 2 becquerels per kilogram? And there's a lot of ways to answer that question. We could do that with a hypothesis test. We'll investigate those in chapter 14 later on in the notes. But we can provide an equally valid analysis just with a confidence interval using the methods right above. So it says, provide a complete analysis of these data, assuming the population standard deviation is 2.95 becquerels per kilogram. I want to put in just one extra wording here. If this was a real, say, homework problem, I would definitely say this. Provide a complete analysis of these data using a confidence interval. I'll be very specific in the homework because we have multiple methods we could use. So let me put that in there for a quick revision, just to emphasize the method we're going to use. And here's our big assumption we're making. We're assuming sigma is that value. Is it reasonable? I would almost want to say probably not. You would wonder, how did they get that value? If the mean of the radioactivity has changed, why hasn't the standard deviation? I would assume possibly both parameters have changed. But for the sake of working through the problem, we're going to make this assumption and just see what happens. Again, if that bothers you, if you feel logically this just doesn't feel right, that's going to be the purpose of chapter 7, where we clean up this assumption. Sigma equals 2.95 becquerels per kilogram, and it's going to go there. So we can definitely calculate X bar. We'll compute Z star in the same way that we did above. Now we have the sample size, so we can compute this entire interval altogether. What we mean by complete analysis is a top to bottom look into this problem where we run through these steps below, where it's going to culminate with a major step, giving a conclusion using the context. Notice we have to say exactly what we're estimating. For using a confidence interval analysis, you need to say in words exactly what mu is. But in a certain sense, we've already done that. That was the purpose of chapter 1 from way back in the day when we did this problem. We made a big deal out of saying exactly what mu was, and sigma, just for the sake of introducing it. But this skill of reading through a context and saying very precisely what mu is exactly is the major thing that's going to allow us to cross through this bridge, seeing what the numbers say and what the real conclusion would be, what a good statement might be in a journal, or if you're, say, talking to someone in the news, what would you actually say based off the numbers you get? Well, this is the whole problem so far, that breakdown of the context. We're still missing one thing. We don't have X bar, so maybe let's start there. Let's get our statistic value. Well, I guess I can't do that any longer, and we'll be in good shape. So you could type in all these values into RStudio. There's no harm going that route, but it is tedious. So for these kind of problems, I'll often have a data file for us. So ccanvas for the example 3 data file to go along with this problem. Let me adjust things just a little bit here. There's a good review on using this method. Go to import from base, pick out your file. We're in chapter 14. Example 3, chapter 14 is the title. We have becquerels per kilogram in bold. That's the quantitative variable, so we're on the right track. Here's its readout. Let me close that. Because this is a data frame with just one variable, probably the first thing I would do is extract that, becquerels per kilogram. I'll call it rad for radioactivity. Gets what did I do there? Example 3, chapter 14. Then $, select becquerels per kilogram. The $sign here again is the hint. That's how you get that value. Then running it, we now have, what happened here? Nothing seems to have happened. Let me see if I can run this again. Control A, Control Enter. Well, that's weird. I do not see my value so far. Oh, no, it's right here under rad. I should have cleaned out the environment. That's a bit of a distraction. Sorry about that. Let me clean the environment just so that we can see exactly where everything is. So let me quickly get this back in. Hit Control A, Control Enter. Okay, it was there all along. It just was too much stuff for me to filter through. So now we've got the radioactivity. Go X bar. To give it a name, we'll get the output of mean of radioactivity. And there it is. Let's decide on a reasonable value to round to. I would say maybe 3 significant digits would do the job. I'm not going to be too picky. I'll go with, say, 10.3. So let's use this value. X bar is 10.3 becquerels per kilogram of dry tissue of this particular tuna. So next, running through the complete analysis process, our author calls this the 4-step method of statistical analysis. I just abbreviated it to complete analysis. I think that does the job. The very first thing is not worth a lot of points when you do this as a homework problem, or potentially even as, say, an exam 2 question. That's just a way to get started thinking about the context. State the practical question indicated that requires a statistical inference. If you see a question mark, that's probably the question that's indicated, but there might not be a question mark like is in this statement here. But if you see it, it says, do we have data that the mean radioactive tissue concentration is above 2 becquerels per kilogram? That's a practical question. You can put it in your own words if you like. That's probably a good idea because now you're thinking more about the context. And that will make the end step, the conclusion, make a lot more sense if you put it in your own words. But you're always allowed to just directly cite that right out of the problem, and that'd be fine as well. Let's go that route just to emphasize this is a fine way to answer the question. So for the practical question, it is this. So just to put down some guidance on doing this in the homework, you can either cite the question like we just did, or put it in your own words. Notice one thing that's pretty important about this, if you do put this in your own words, the confidence interval is right here where the red dot is, and it's expanded form. It's kind of uglier that way, but it emphasizes what we're doing. We're estimating mu. So when you go to write out the practical question, and when you give the conclusion, you have to say mean somewhere. And you have to tell me the mean of what specifically? The mean of the radioactive tissue concentration. So those would be elements that have to appear in the practical question, but more importantly, the conclusion is not about one particular fish. It's about the average value or the mean value of all of the fish of this kind, that Pacific bluefin tuna. So again, if this was maybe a 12-point problem in a homework question, that's 1 point. It's not major, but it's a way to kind of make us really think about the context, get us on the right track. Any questions so far, folks, with the state part of the problem? Okay, the planning phase is usually where we do a lot more thinking. It's a good idea to read these problems maybe multiple times, make sure we know what the population is and what the parameter will be. Essentially, what we're doing in the planning phase is going back to this. We must describe mu very precisely, or else our conclusion is just not going to look right. So let's come down here. When it says define the unknown parameter, that means we're not talking about sigma any longer. In fact, we assumed a value for it, 2.95. We're talking about the thing we're about to estimate, mu. We have to use the context. And some elements of the context are very, very important because if I say mu is the mean radioactive cesium concentration of all Pacific bluefin tuna, that wouldn't be it. It sounds like we're talking about the population as it stands now in 2026, but this study had a massive temporal component. This was all about the meltdown and what happened specifically 4 months after that meltdown of 2011. So that's what we're really analyzing. That's our population. It has a geographical component, but a temporal component at the same exact time. So always be pretty careful with this parameter. Make sure when you write it down, you reread the study again, make sure there's no elements of the context left out. And I would phrase it this way. Mu is going to be equal to, you could say the mean or the average. I would consider those synonymous. I'll go with mean on this one. It's going to be the mean radioactive tissue concentration. Here we're talking specifically cesium-134, 137. But again, you don't have to write down the problem verbatim. We can allow that to mean what we are emphasizing is the tissue concentration, the radioactivity of it. So the mean radioactive tissue concentration for all, when we say all here, we're trying to emphasize we're talking about a population. And the population is all Pacific bluefin tuna. It's nearby the coast of California. we have to make a judgment call. Is that important? These are extremely migratory fish. And if they are only sampling nearby the coast of California, probably we should bring that in, much like, say, in this problem, if we're talking about people have a specific peripheral arterial disease, we're not talking about the ABI of all women like we did on example one. It was a particular kind of condition for these women in the population. So let's mention that geographical component, all Pacific bluefin tuna caught off the coast of California. And that's not the whole story because, again, there's a very critical time component. We want to know what happened to the radioactivity, specifically 4 months after the meltdown. And I'll just abbreviate by saying the meltdown of 2011. 4 months. Oh, hang on. I think I made a mistake there. If I say all Pacific bluefin tuna caught off the coast of California, that's a pretty silly mistake. I'm talking about the sample, that's X bar. So let me eliminate that statement there. All Pacific bluefin tuna, let's say nearby, the coast of California, 4 months after the 2011 meltdown. Okay, we got through that. And watch out for that mistake right there. I had to backtrack on. Again, it's a good idea to reread these a couple times. If I said caught off the coast of California, I'm talking about the 16 tuna, but the population is all of them. That just happens to be the one they were able to get. The last thing we have to do is sometimes kind of uncomfortable in a certain sense. We are ourselves going to choose the confidence level that we think makes sense. Most of the problems are going to say use a 95 or 99% confidence, but occasionally it's going to be all up to you. Any volunteers for what sounds like a good confidence level on this one? These wide open questions are kind of weird in a certain sense, right? Because if someone shouted out 97%, that's valid. We can absolutely do that. Might seem a little bit weird, but logically it's completely sound. Someone said 99% confidence. That would assume you really want to make certain that you get great accuracy, high percent chance of the method working, really getting mu. If you said 90%, well, you're going to get a narrower confidence interval, but you're trading the precision there for the accuracy in the method. If you're just not sure if this problem doesn't resonate in one direction or another, 95% is a decent value to go with. Make sure, though, if you go to put this in the calculator, you're actually using 0.95 rather than the percentage. So the next thing we'll do with this problem when we're back a week from today after the exam is we'll see if the conditions are reasonable. How bad do these data really look? Are they highly skewed? Or is there a reasonable mass symmetry? Then we'll carry out the method. That means we'll just put these values all together, compute the interval. And the very hard work with every one of these problems, whether it's a confidence interval or hypothesis test, is to give a very strong, all-encompassing conclusion, mentioning any limitations that come up. But we did the major hard work when we said exactly what mu is. We can basically come back up here with mu in the middle, and the two numbers we've come up, we'll say with 95% confidence, mu, you have to read out what it is, that's the annoying part, will be between these two figures that we're about to get. Again, we'll have to come back to that a week away from today, but we did the hard work getting started with this one. And hey, discussing what the parameter is, that's good review for exam one anyways. These are tough problems. That's why we made that basically the first major question of the whole semester. These would be good ones to come back to as well for studying on exam one. Well, any last questions at all, folks, before we call it a day? Okay, well, thanks for your hard work, folks. If any questions come up while you're studying, please don't hesitate to reach out. Even if it's on the weekend and you're sending the questions, say Saturday at 3 a.m., anything weird like that, I'm checking my email essentially every single day of the week during the semester, and I will get back to you first thing in the morning. But have a great weekend, folks. I'll see you all in the in-person section in the class on Monday. And everyone else, I said Thursday a couple times, sorry. We'll meet again on Wednesday. Take care.